Hi, this is Mrs. Westmoreland, and this is a lecture on solution stoichiometry, which includes limiting reactant, and it will help you with the summary for precipitation reaction questions in your precipitation lab. So here's our question. We want to calculate the mass of precipitate that will form when we combine 20 milliliters of 0.11 molarity sodium sulfate with 10 milliliters of 0.38 molarity lead 2 nitrate. So the first thing we have to do is write the balanced double replacement reaction. And so since the reactants, as described, are ionic compounds, we need to balance out the charges for their chemical formulas. So sodium +1 ion from group 1, sulfate polyatomic ion with a formula SO4 - 2, lead with a +2 charge because of the Roman numeral 2, and nitrate polyatomic ion with the NO3 1- charge. Since sodium sulfate is described as a solution, its physical state signifier is AQ, and also since we're told that it's aqueous lead 2 nitrate, it's also AQ for its state signifier. So we balance out the charges of each of the reactants and we include the state signifiers for each reactant. Now, because this is a double replacement reaction, this is the wife swap of the types of reactions. So the positive ion from the first compound, the sodium, is going to combine in the products with the negative ion from the other compound, the nitrate. And those also are going to balance out charges. And then the lead 2+ ion from the second compound is going to combine with the sulfate -2 ion from the first compound to make our two new products. Now we need to consult the solubility rules to determine the state signifiers of those products. We don't have any clues in the question. So when we consult the solubility rules, we see that nitrates are soluble no matter what the positive ion is. So the sodium nitrate would be AQ, aqueous, state signifier, soluble. And sulfates are soluble category. However, the exceptions for sulfates include lead. And so since it's an exception, it will go the opposite of the normal rule. So since the normal rule for sulfates is soluble, the rule with lead will be insoluble, which makes its state signifier solid. And then I need to include the coefficient to create the balanced chemical equation. Next, we need to identify the measurements given in the question. So I've just written those measurements for each of the reactants underneath the substance in the balanced chemical equation. So I have 20 milliliters of 0.11 molarity sodium sulfate and 10 milliliters of 0.38 molarity lead 2 nitrate. And because we're given two measurements of two different reactants, that's how we know this is a limiting reactant problem. So because it's a limiting reactant problem, we're going to need to do the stoichiometry twice. And because this in particular is solution stoichiometry, we need to remember that the capital M for molarity should be changed into a fraction style ratio, and the other given number is going to be the dimensional analysis setup. So you can see that underneath each of my givens, I've written the two fraction style ratios that can be created from the molarities that are given. So anytime we see the capital M, we can change it into a fraction style ratio of moles, that many moles over 1 liter, or 1 liter over that many moles. And I've done that for each of my molarities. Therefore, my setups will be, since I want to know the mass of the precipitate that will form, since lead 2 sulfate, the product is the solid product, is my precipitate, I'm solving for that. How many grams of lead 2 sulfate will be equal to, and we have two setups, one equal to 20 milliliters of the sodium sulfate and the other equal to 10 milliliters of the lead nitrate. So in my map of mole land, I'm starting my dimensional analysis with volume of a solution in liters. So since I'm given milliliters, I'm going to have to change to liters. But really I'm over in that top corner of the map of mole land. And so first thing I need to do is get to moles, and you can see that on this map, the connection that allows me to get from liters to moles is the molarity itself as a fraction style ratio. So by using a fraction of the molarity, I can solve for moles of the chemical that I have measured, the reactant. Then, using the balanced chemical equation, I can cross the mole ratio bridge to find moles of the product, which will be my lead sulfate precipitate. And then I can use the molar mass of that product to solve for the grams of the precipitate. So the highlighted pathway is the pathway I'm taking to solve each one of my dimensional analysis setups. So here's the first one. I have how many grams of lead 2 sulfate would be equal to the 20 milliliters of sodium sulfate that I've measured out. So first fraction is the conversion from milliliters to liters. Next, once I have liters, I can use molarity itself in the fraction style ratio to go from liters to moles. Then I cross the mole ratio bridge from moles of my starting substance, the sodium sulfate, to moles of my ending substance. And then finally I go from moles of lead sulfate to grams of lead sulfate using its molar mass. And when I do that mathematical calculation, I get 0.66 grams of lead 2 sulfate. And I round to 2 significant figures because when I look at the numbers given to me in the problem, 20.00 has 4 and 0.11 has 2. I want to limit my answer to the smaller of those two. And that should actually probably be 0.67 when I round up. Now I'm going to do the same thing, but this time with the other dimensional analysis setup. So solving again for grams of lead 2 sulfate, but this time starting with my 10 milliliters of lead 2 nitrate. So first convert from milliliters to liters, then use the molarity of the lead 2 nitrate as a fraction style ratio, then cross the mole ratio bridge between my starting substance of lead 2 nitrate and my ending substance of lead 2 sulfate, and then finally use the molar mass to get to 2 grams of lead 2 sulfate, which in this case, when I do the math, I get 1.2 grams of lead 2 sulfate. And again, I use 2 significant figures. 10.00 has 4, 0.38 has 2. I round my answer to the smaller number of sig figs. So when I compare my two answers, setup 1 gave me 0.66 grams of lead 2 sulfate. Setup 2 gave me 1.2 grams of lead 2 sulfate. So I'm going to choose the smaller answer, which is the 0.66 grams. And therefore, the sodium sulfate is my limiting reactant. So here's an animation to sort of help you visualize what's going on in the solution as the precipitate forms. So if we have a soluble ionic compound in water, we can visualize it as breaking apart into ions as it dissolves in water. And so when we have two different ionic compounds that are both soluble in water, you can see them all dissociated or separated into their ions. However, when the chemical reaction occurs as the particles collide with each other, the combination that is insoluble will join together and kind of settle out to the bottom of whatever container we have, and that is the precipitate, while the other ions will remain suspended in the solution. Thank you very much for listening. Good luck with your lab.